atmospheric water exists anywhere you are on the Earth, and sorbent materials are capable of harvesting it anywhere on Earth. The next step, or another way that we can exploit these sorbent materials is through dehumidification. So when air cools, it's able to hold less water, and what this does is it increases the relative humidity. So this is a large problem for indoor spaces as well as people living in those indoor spaces. It can cause quick degradation of indoor spaces. It can also cause a ton of respiratory problems for humans. So what HVAC systems do is they subcool the air colder than it should be, colder than what you want to deliver it as. They're gonna condense water and then they're gonna reheat it and put it into the environment. What we can do with sorbent materials is dehumidify it before we put it through our evaporator, which is going to cool it off. And what this can lead to is about a 25% energy savings in these AC systems. And the last way that we can exploit these sorbent materials is thermochemical energy storage. So the way that thermochemical energy storage works is we first are going to start with a hydrated material, and we're going to put heat into the material, and what this does is it separates the material from the water. So now we have this potential that's stored in the material. We can keep it for an indiscriminate amount of time, and then when we're ready to harvest the heat, we can just expose the material to water, and now we get this heat release from the material. And what this does is it can levelize our thermal demands from our system, or we can follow those intermittent loads that we talked about in the first slide of when we can get jet heat mismatching from when we want to get the heat. So there's these different applications have different demands. The first and most pressing is obviously what they're looking for. So atmospheric water harvesting is looking for water. Dehumidification, obviously we're looking for dry air. And thermochemical energy storage is looking to get the heat out of the material. And these have really different engineering demands that they require from the system, and they lead to very different geometries and also design choices that we make. So for atmospheric water harvesting, we want really high air velocities. And what this does is it maximizes the reaction rate that you have. So the surface of the air is always seeing this really the surface of the material is always seeing this really humid air. Dehumidification, on the other hand, we want low air speeds because we want to maximize the amount of time that our humid air is within our device. So we want to get the lowest relative humidity out of our device. At the same time, this has a negative issue because we're now going to minimize what are driving forces of our reaction, this high humidity in the air. And then finally, thermochemical energy storage is highly dependent on application, and then it's also can operate in purely vaporous environments. So for this presentation, we're going to mainly focus on atmospheric water harvesting and dehumidification, just because they're a lot more specific and they're a lot more easy to apply in our lab setting. So now that we've kind of looked at what are the different demands, what are the different geometries, what do they lead to the design, we're going to look at what's the best sorbent material. So we're going to compare 3 sorbent materials. We're going to compare MOF, zeolite, and pan lithium chloride. And the first thing I want you to notice is that on this left hand of the axis is going to be the MOFs and zeolites, and those are going to have an uptake of about 0.5 grams of water per grams of material. And on the left side, we have the hydrogel uptake, which is going up to 5.5 grams of water per gram of material. So as you can see, it's a significantly higher uptake than we're going to get out of the zeolites and MOFs. And the other thing I want you to notice is the curvature of these. So we have these two, like an S-shaped curve and just like a purely like almost logarithmic curve versus this nice long exponential curve. And what this allows us to do is use low-grade heat to regenerate our material. So really this is something that's going to be abundantly useful. It's really a hot topic in energy systems today is how can we harvest this low-grade heat that's really abundant in our society to do something productive. And what we can show is with this curvature, we're able to use low-grade heat to bring a 60% relative humidity down to a 15 or 30% relative humidity. And from that, we can get a useful work out of it. We can adsorb and desorb water. And the next thing I want to point out is the cost. So MOFs are capable of moving this curvature over to between the 30 and 60 range, but they have really high costs. They require rare earth elements that are really difficult to source, and they require really complex manufacturing methods where these hydrogels, as we'll go into, are actually quite easy to manufacture and are really stable. So that's kind of why for the rest of this presentation, we're going to mainly hone in on hydrogels and how those can be used for our atmospheric water harvesting and dehumidification. So this presentation, we're first going to start on a material level. We're going to go into the thermodynamics and kinetic analysis. Then we're going to prove our thermodynamic and kinetic analysis through characterization. Finally, we're going to go to a component level. So with these equations that we've gone from our characterization thermodynamic analysis, we're gonna move into a model, and from that model, we're gonna optimize our geometry based on that model, and then finally, we're gonna go into experimental validation and kind of prove that we are able to have a meaningful device come from this low-level material level analysis. So I first want to start out with thermodynamics and kinetic analysis and explain what those mean. So thermodynamics is the steady state and it's the energy states of our material. So it tells us how much water our material is possible to uptake, how much heat our material is possible to release into the environment. Where kinetic analysis is going to be how quickly it happens. So that's going to be the police. It slows down and makes sure that our reaction happens in an amount of time. And for these hydrogels, generally we want to increase our reaction rate to make them as quick as possible and increase our kinetic rate. So I've kind of leveled in onto these hydrogels from a big picture, but I want to start with what are hydrogels fundamentally. Hydrogels are composed of three main components. They're first going to be these hygroscopic salts. So for our experiments, we use lithium chloride and calcium chloride. Lithium chloride is an ideal material. It has a significantly higher uptake than calcium chloride, but calcium chloride is significantly cheaper. So depending on our application, we're going to use either of the two salts. The next thing we're going to look at is the polymer chain. So the polymer chain acts to contain our solution. And it's the ropes in a netting, if you think about it like that. So it's going to contain what we're trying to trap in the net in it. And the crosslinker is going to be the MBA. So the crosslinker is the knots in the net. So the more knots we have in our net, the tighter the mesh is going to be, the harder it's going to be to pull apart. But that also means that we can carry less stuff in our net. Where if we have lower cross-linking, we're going to have this really flexible material. And you can see it between these two images. We have a really high cross-linking material and then a really low cross-linking material, and it looks almost like fluffy. So you can really change the modulus elasticity of the material just by modulating this cross-linker term. And we'll go into kind of the macroscopic effects that we get from it too. So kind of, if I talked about salts, I talked about polymer chains, and you notice I didn't really mention the polymer chains we're doing a whole lot for our uptake. So why not just use pure salts? So pure salts run into a couple issues. The first and most pressing is the deliquescence step. So what the deliquescence step is it's the transition from a solid to an aqueous solution. And when salts undergo this, something like this is going to fall apart, right? It's going to become an aqueous solution. So you have to keep it in below that deliquescence point. And that limits your operation. If you choose to go between the deliquescence, above and below deliquescence, this will cause large crystallization, and then you get these really slow, bad kinetics just from the from these large crystals needing to have a chemical reaction happen to kind of dissolve them. And we'll go over kind of other advantages of the lithium chloride, but they are used and they have their own purposes. They're really good at some things, but for our case, we're going to really focus on using these salt-loaded hydrogels to fully exploit the hydrophilicity of the salt. So the four parameters that we're going to design our hydrogels with is we're going to look at cross-linking density, and we're going to define this as the amount of grams of MBA we have per grams of polyacrylamide. We're going to have our initial water content. So we're going to define this as our initial volume fraction of polymer, just to normalize it, so we don't have to worry about having different salt and water contents with the same polymer volume fraction. The next is the salt loading. So we're going to go from 1 gram to 8 grams of lithium chloride and also calcium chloride. And that's going to be defined as the amount of grams of lithium chloride we have per grams of polymer. And the next, we're going to go to our salt species, as we talked about. Lithium chloride and calcium chloride are going to be the two that we looked at, but any hygroscopic salt can be used in these polymers. So the characterization methods we use is we're going to synthesize the gels, and then we're going to put in a DVS and a TGA DSC, and I'll go into what those are in more detail later. And then finally, we're going to go to this custom centimeters scale wind tunnel, and we're going to see the swelling in the hydrogel. And this allows us to refine it, the swelling. So swelling is something that's been overlooked previously in literature. It's been seen as a secondary effect that doesn't have a significant effect on the kinetics or the enthalpy of the material. And that's because a lot of the experiments have been happening in this really low cross-linking range, which is great for material properties, but they're not realistic on what an actual machine or a device would ever implement because of their low lifespan. So we're gonna go and see in these high cross-linking domains, is there an effect on swelling on our enthalpy, on our uptake, and how does that inform our design of our hydrogel device, our hydrogel device? So there's the thermodynamics of salt-loaded hydrogel, where this is going to be defining what's our uptake. How much water do we get per gram of hydrogel? So we start with this thermodynamic equilibrium term, which means that we're going to define our equilibrium when the chemical potential of the gel or the water in the gel is equal to the chemical potential of the water in the environment. This is defined, just the chemical potential of the water in the environment is defined by this RT, Ln, RH term, and the chemical potential of the gel is defined by these four main components. Our ion water component, which is going to be defined as the non-linearities of mixing between salt and water. Our mixing term, which is just the mixing of the polymer with our solvent. The polymer solvent term, which is the enthalpy of mixing, which is defined by our Flory-Kai parameter. And then our elastic mixing term. So this is how much does swelling decrease, or how much does our crossing decrease our uptake? And this is really an important term that we've defined in this characterization. So the next, we're going to look at the enthalpy of the hydrogels. This is how much heat is released as we absorb water. So there's two main components of this. There's first going to be the phase change energy of water, that 2,400 kilojoules per kilogram we mentioned earlier. And what this does is it condenses, and it's going to release heat into the environment when we condense, and it's going to absorb heat from the environment when we evaporate. And then the next thing that's important is this water-ion interaction. So when these salts salts attract water, they create these dipole ion interactions. And these have these bonds, and the bonds have energy, right? So when we put the bonds together, we're going to release energy, and when we take the bonds apart, then we have to input energy to break the bonds. So this is this enthalpy of dissolution. And we'll see the enthalpy of dissolution is highly dependent on our mass fractions when we mix the salt and the water. So what we do find is that by an order of magnitude analysis, we see that our enthalpy of mixing, our enthalpy of polymer solvent, and our elastic enthalpies are orders of magnitude lower than our water ion term and our latent heat term. So we're able to neglect them and assume that this H sort is just equal to the HFG plus HWI. And then finally, we need to look at the kinetics. We need to find, great, we have these derivations for the thermodynamics, for the heat, but how do we determine the kinetics? How quickly does the reaction happen? So what we do is we define this G term, which is going to be our mass transfer coefficient, and we have a linear driving force defined by our relative humidity minus the activity of this hydrogel. So as you can see, it's going to define how much of the external humidity is going into the hydrogel. The next, we have this hydrogel swelling term. So this is extremely important for both our kinetics, and we talked about it in our derivation too. But we need to find how much our hydrogel swells as it uptakes water so we can fully define our length scales. So what we do is we take this, for our experiments, is we're going to assume that we have 1D swelling. And how we do this is by securing the hydrogel to a substrate. And then so we have this lambda naught term, and that's this initial swelling term we get. So that's after we swell the gel freely, after making it and equilibrating with our environment, we're then to secure it, and now we have 100% of our swelling is going in this transverse direction, this lambda XX direction. And from that we define as this term right here. And then finally we have our diffusion within the hydrogel. So what we do is a modification of Fickian diffusion. So we assume that we have concentration gradients within the gel, and those gels are what's promoting our diffusion within the gel. So we define our D effective as a function of both our polymer mass fraction as well as our lambda XX term, which is our swelling term. And we'll go through and fully define these later when we go and characterize it. So now we're on to the characterization step. We've done all this great work on thermodynamics and kinetic analysis. But how do we actually prove that it exists in reality, right? So the first way we're going to do that is through our dynamic vapor absorption device. So what this is a vacuum pump attached to a turbo vacuum. So we can get this really low millipascal vacuum. We then have this reservoir, and that reservoir is going to feed the humidity into our device. We have a mass flow controller that's going to control how much of the humidity gets into our device, and from that we can modulate how much humidity our sample is exposed to. Then we have this microbalance, and the microbalance is going to tell us how much our mass changes. So the first step we do is we heat up our device. We're going to raise it to about 150 C, and this is all under vacuum. From that, we're then going to cool it to 25 C. We're going to, and still under vacuum, we're going to get that initial mass. And what this represents is our dry mass of our material. Then we're going to expose it to 10% relative humidity, and we're going to let it equilibrate. And then we're going to continue this for 20, 30, 40, 50, all the way up to 80% RH. And as you can see, we're going to get the mass change. So we're going to get our initial mass right here, and then we can find a mass at, let's say, 40%. At the 40% pressure, we find when it equilibrates, and our equilibrium is defined as, I think, about a millionth change in mass. So we're going down to these really, really low scales. We're taking a really long time to get these really well-defined masses, and we can say this is the uptake. From this, we find the uptake by subtracting the mass at the given RH by the initial mass, and then dividing it by the initial mass. That gives us our uptake. At the same time, because we're in a purely vaporous environment, we're able to also find the diffusivities. And we find the diffusivities by finding the time scale from let's say 30 to 40, and then we do this linear driving equation to find what the tau is. So this is how we're able to find the uptakes, and as you can see, our uptakes match our theory extremely well. We have extremely close matching for 1 to 8 grams of lithium chloride per grams of polymer, as well as 4 grams of calcium chloride to grams of polymer. And then we also are able to find that this cross-linking term, which is previously considered insignificant, has a significant effect on the gel's uptake. So while salt is dominant, this cross-linking term is still a significant design parameter that needs to be accounted for when you're building devices with these gels. And as you can see, it's pretty marginal below that 50% RH. So this is at 30% RH, we're getting a less than 0.1 change in uptake per gram of hydrogel. Where at the 60% loading, or 60% relative humidity, we're now getting a 0.28 grams of water per grams of hydrogel change. So now it's significant. So depending on the uptake of your hydrogel, it has a significant effect on, or depending on your uptake, or what your relative humidity you're operating in, it has a significant effect on what cross-linking you want to have for your device. The next thing we look at is the relative humidity. We look at, the next thing we look at is the diffusivities. So we define the diffusivities by, again, with our timescales. And what we found is that increasing cross-linking decreases our diffusivity, which is as expected. You're gonna have this tighter mesh. So now the water has to go through these tighter holes. You have smaller sizes, so everything's getting squeezed more really. We find that this chemical absorption step significantly hinders reactions. So this is actually kind of a misnomer. What we're getting is that there's now a chemical reaction that's occurring, this deliquescence reaction, and it's not really that our diffusion is this slow, but our chemical reaction is significantly hindering what our effective diffusion is measured as. And then the next thing we find is that increasing our relative humidity decreases our chain mobility, which is a harmful effect on diffusivity. So the next thing that we're going to characterize is our enthalpies. We're going to first initialize our samples at 150 C in an oven, and we're going to take them into this device, and we're going to cool them to 25 degrees C. We're then going to introduce humidity levels varying from 15% to 75% at increments of 25 degrees C, or at increments of 15% at 25 degrees C. And what this device is able to do is we're able to control relative humidity through this humidity module. We're able to find our heat flux from this pan. We have a heat flux sensor on that pan. And then we also have a microbalance. And what this microbalance is able to do is we're able to find the change in mass. So what we're able to do is integrate our heat generated to our change in mass, and we're able to find how much heat we're generating per unit mass. So what we found is that the cross-linking has a fairly insignificant effect on the enthalpy of the material. And we also found that calcium chloride has a slightly higher enthalpy than lithium chloride. So this does look kind of weird to someone who's worked with the salt materials a significant amount. But because the calcium chloride is closer to its deliquescence step, sure, the total energy is lower from a dry state to this 60% state, but we're comparing from 45 to 60% swing. So we're really looking at just this really small swing range, and in this swing range, calcium chloride is going to have a higher enthalpy, and this aligns with theory, as we pointed out. The other thing we notice is the same with the enthalpy of salt. We see it approach the enthalpy of the latent heat of water as we reach this 80% RH. So both of these align with kind of what our theory dictates. So we're kind of happy with the results here. The next thing we're going to look at is the physical effects of swirling and also the effects on kinetics. So the way we do this is by creating this millimeter scale wind tunnel. We're first going to cast our hydrogels into 5 centimeters by 15 centimeter PLA molds. We're then going to adhere the hydrogels to the aluminum plate, and then we're going to have an airspeed of 3 millimeters per second and stabilize for 14 hours. So what this gives is us a solid initial state, Then we're going to set the chamber to 60%, and we're going to track the swelling of the hydrogel, as you can see here, as well as the mass change with the scale right there. So how are we tracking the change in the hydrogel height? We're doing that using a MATLAB computer vision tracking pipeline or code. What it does is we have a user-selected top and bottom boundary, and then what we do is we sample 10 points across the surface of the hydrogel, and then we use pixel intensity to find where's that difference. So as you can see, it's significantly lighter in this range versus this range. So what we're able to slowly track where the gel is at any given time by finding the mean of those pixel heights. And overall, we found really good agreement with our kinetic model. We found an average of 2.4% error in our absorption kinetics for mass and about a 4.1 in the swelling. And this 4.1 can be kind of can be written off as differences in the gel height. So because we aren't going to have a perfectly smooth surface on the height of the gel, these fluctuations are going to cause deviations from our model. So overall, both of these are well within our realm of reasonability. So now that we have this great characterization, we are able to predict what the gels do, let's actually put it to practical use. So as we've said, like cross-linking has just hurt most of our, cross-linking has hurt both our kinetics and our thermodynamic uptake. So why wouldn't we just go to super low cross-linking like a lot of theory does? And the most important thing is this lifespan. So low cross-linking hydrogels have significantly lower lifespans than high cross-linking hydrogels. At the same time, they have slightly worse, but at the same time, they have slightly better uptake and slightly better swelling. So really, this cross-linking balance is going to be dictated on what our device demands. If it's a device that's cycled a significant amount of times, we're going to increase our cross-linking. And if it's a device that's not cycled a ton, we're going to have a really low cross-linking to just get like the best out of the couple times we do cycle it. The other thing to notice is our optimal hydrogel salt loading. So what we see is that as we load more and more salt into our hydrogel, we get an increased restriction of our uptake. And this increased restriction decreases how much swing we get out of it. So the swing is the change in mass from one relative humidity to another relative humidity. And what we're able to find is that from 3.5 to 4 grams of lithium chloride per grams of polymer is where we get our optimal swing difference. So what we found is that a 4 gram per gram hydrogel with a 6 milligram MPa per gram of acrylamide, cross-linking is going to be our optimal hydrogel, and we're going to proceed through the rest of our material level or rest of our device level analysis with this polymer or this hydrogel. So now we're on the component level. So we're going to start with this model and optimization component. So the design, we're going to have two trade-offs. We can start either with this super thin hydrogel and like a super low packing ratio of how much hydrogel we have in our device, or we can start with this really large block of hydrogel, this large chunk. And this large chunk would have really great energy density. We'd have about 100% of our device was just filled with hydrogel, so we can get these huge swings over these really long periods of time. But that's not super useful, right? If it takes us 5 days to cycle our device, there's no workable output that we can get out of it. At the same time, if we have these really thin layers, we don't get enough material out of it to really make it suitable. So what we do is we converge on this fin-in-tube heat exchanger. We use these thin-coated hydrogels on these small plates to get high packing densities, as well as getting these air gaps between them, so we minimize our convective resistances. At the same time, we're going to have to optimize this, right? So how thick do we want it? Do we want it the super thick hydrogel or the super thin hydrogel? And to solve that, we're going to use a multi-physics solver console and do a fluidic thermal model of our device. We're going to input our hydrogel activities and our diffusivities from our previous thermodynamic analysis, and then we're going to use a gradient descent to find the optimal geometry. So we're first going to start with our conservation of vapor in the air. So we have an accumulation term, an advection term, and then a molar flux at our surface. The molar flux through the gradient. We're going to have our boundary conditions. We're going to have that boundary condition we defined in our thermodynamic analysis on the surface right there, and we're going to assume that there's going to be no mass flux on any side, or really on the top surface, and there's no mass flux into our pipes, right? We're going to assume those pipes have zero porosity, which is fine. And then there's going to be a conservation of bulk of the hydrogel. So we're going to have to conserve, if water goes into the hydrogel, it can't magically disappear, right? So what we do is we have these no flux boundaries on the left side, bottom, and right side, and we have, again, on the surface, we have the coupling to the other conservation on this side. So if water is leaving the hydrogel, it's going directly into the air. On the same time, we have to conserve heat. So again, we have an accumulation, advection, and conduction term within our air domain of the device. And we have a thermal flux on the surface. So one approximation we do make is that 100% of our thermal flux is going to be happening on the surface. And that's because we use a lumped approach to our hydrogel. We assume that we're going to have an equal amount of salt loading in our hydrogel. And we'll see these approximations are fairly valid on the second, when we do the physical analysis. We have a conservation of energy in the bulk of the hydrogel. So energy can't just magically leave the hydrogel. If it's going one place, it needs to go somewhere else. And what we do is we have this generation term on the surface, and we have these no flux terms on the bottom and left and right side. So we have our two applications, right? We have an atmospheric water harvesting application and a dehumidification application. And these two applications have really different demands. One's going to demand that we have the strongest driving force the whole time, so we're always exposing it to new air, while the other is going to really want to have slow air moving through it to have the minimized relative humidity at the outlet. So how can our geometry reflect this? And one way that we chose to optimize a dehumidification device is by adding the sinusoidal nature to it. So what it does is increases the residence time of the humid air in the device. And what this does is it really minimizes the outlet relative humidity. So our design parameters are going to be the amplitude of that sine wave, the frequency of that sine wave, as well as the length of the air, so the height of the air, and the length of the gel. For atmospheric water harvesting, we want these really thin layers, we want fast-moving air, and the way to do it is just through a flat plate. So we're going to just use a kind of flat plate sine wave, or a flat plate heat exchanger, just kind of a normal tube and fin, as you'd expect out of any normal heat exchanger. So to analyze that, we're going to use a gradient descent. We're going to start with a 4 gram per gram air gap and go all the way up to 8 gram per gram air gap, and we're going to find what's the highest mass gain we can get, and then we're going to go adjust it for the height, the length of the gel. So we're going to start with a really low gel height, and we're going to go to a really high gel height. And what we found is that you want about a 5 millimeter air gap, and you want about a 2.5 millimeter gel height. So, and what we're able to find is we're able to produce 644 grams or kilograms of water per meter cubed of material per day. So that equates to about 32 people's daily water needs, which shows that with a relatively small amount of space, we can produce a significant amount of water. That could really have an impact on a community that's struggling to find clean and drinkable water. For the sine wave heat exchanger, we have a significantly more complex geometry, and because of that, because of the nonlinearities, we're going to have to use this neural network to get our gradients. So what we do is we use our four parameters as our inputs, and as our output, we use the concentration of vapor on the outlet surface. What we're able to get is a 0.92 R squared. So this shows us that we're not overfitting, and we're predicting with really high certainty. So we're predict within a 0.001 concentration, so moles per meter cubed, of what the outlet relative humidity or the outlet concentration is going to be. So with this concentration, we're going to do a gradient descent. So we analyze our neural network doing a gradient descent, and we're able to find that the optimal height of 1.3 centimeters, or optimal amplitude of 1.3 centimeters, an optimal frequency of 153 meters, or 153 waves per meter. We found a gel height of 2.1 millimeters and a height of air of 5.3 millimeters. And what this showed is that we're able to reduce it from our average. If we had just taken a random guess on what our amplitude, gel height, and length should be, we gained about 40% efficiency on our device. So pretty good optimization. Finally, so we have this COMSOL model, but we need to actually validate it in the real world. Is our COMSOL model something that's workable in the real world, or are we missing some kind of physics? So the way we design this is with a chiller. So we have a chiller that's going to heat or cool our water. We're going to have feed water, return water. To get our mass balance on the air side, we use two relative humidity sensors, two on the inlet and two on the outlet, and we use our temperature. And from that, we get our humidity ratio on our inlet and outlet. And using our airspeed, we can define how much mass is going through our system. At the same time, we have this scale, and that scale is going to tell us how much mass is staying in our system. So as you can see, this is the actual photo of the device. It's in the humidity chamber, so we can control the environment. We have our data acquisition system and the actual hydrogel coated heat exchanger. So this is what the atmospheric water harvesting fins look like. So as you can see, we get about a 2.5 millimeters of hydrogel, and then about 5 millimeters of air. And the way that we were putting this together is through retaining rings to secure everything in place. For the dehumidification, in order to make sure that we don't get any thermal leakage, we put in a significant amount of insulation, and then we have this single pass of hydrogel fin and air flowing through it. So how do we prepare and actually manufacture these hydrogels, or hydrogel-coated heat exchangers? The first step is we're gonna have to cut the metal. So we cut it, and then we're gonna have to spray it down with a coating just to make sure we don't get any rust. We then are gonna synthesize it in this flexible resin. From that, we're gonna put down an adhesive, put the flexible resin on top of it with the hydrogel on the bottom of it, secure it to the plates, and then remove it. Then we're then gonna cut the pipe holes, and we're gonna repeat that for both sides, as you see here. Once we cut the pipe holes, we can then put our pipes through, and we're securing it using these retaining rings. So ideally, we'd be using tube expansion, but I'll go into tube expansion. We didn't have a tube expansion device, so this is kind of what we may do. And we'll see later why a tube expansion device would have been nice. And then finally, once we have our 5 layers of hydrogel all in there, we can then put it in our housing device, secure it all together, and then seal it off so we don't get any leakage. So to analyze the inlet temperature, outlet temperature, and humidity ratios and mass, we used our sensor data. The first thing is we're able to see this really nice cooling off. So because we use cyclical stability, we start at a hot heat exchanger device, and it's gonna cool off for our initial phase. And then we see this slow cooling off. So you can see kind of 2 time scales. And what this shows is this is our cooling off, and then we get this thermal generation due to the condensation on our device, that heat absorption that we expect to see. And on the flip side, we see the exact same effect, right? Where we see the initial regeneration stage, and then we see this exhaust of the evaporative cooling. For the humidity ratios, while these do look different, because we have we have a really high airflow during the adsorption phase and a really low airflow during the desorption phase, we actually get the same swing in mass as you see on the left side. So we have about a 1.36% error between our airside mass conservation or scale conservation, and about a 2.6% error in our time scales, which is well within our expected errors. So we can say without any uncertainty that our scale is measuring right, we have correct relative humidities, and then we don't have significant leakages in our device that'd be causing erroneous results. So compared to the model, we get a 13.53% error in mass change and a 6.5% error in time cycle. And what I really want to draw your eyes to is this kind of curvature right here. So at first we had a really nice curvature, but then we almost hit a wall, and it looks like we hit a wall. And what that might be a result of is either uneven surfaces. So these uneven surfaces are reducing or creating these elongated mass transfer resistance inside our device, or it could be a result of the microscopic diffusivities not correctly aligning with what the macroscopic diffusivities actually are. The next thing that we have is this 40% temperature gap in our surface temperature versus our pipe temperature. And what this shows is that we have a significant mass transfer resistance on our hydrogel coated pipes. And what this shows is that because we used these retaining rings to secure our pipes to the hydrogel, we get these small gaps that are either going to be gel in between those retaining rings and the plates, or just like an air gap between the retaining rings and the plates. And what this causes is a really strong contact resistance between our pipe. This is actually a really good sign. It's a promising sign. It shows that these hydrogels can be used to exploit temperatures at maybe 60 to 70, right? If they're manufactured with industrial design parameters. And to me, this shows that we can use these devices to harvest from something like a data center or low-grade heat that's readily available almost anywhere in the world, right? Or anywhere really in an industrialized society. So benchmarking with literature. So we have this device, that's great. Where do we compare it to everyone else? First, we show that multi-cyclical devices have significantly higher uptakes than these solar-driven devices. Even so, in these solar-driven devices, we see planned lithium chloride has a higher uptake than either zeolites or other hydrogels. The other thing that we were able to show is that we were able to get these really high uptakes without this really high-grade heat. So in this experiment, we used 150 degrees C So this is really high grade heat, not heat that you're gonna just have lying around. It's gonna be high temperatures that you're gonna have to use as like you're gonna have to input energy to get out of it. While our atmospheric water harvesting at ADC is something that's readily available in either industrial or domestic uses, and that we can use this lithium chloride, that we can use these lithium chloride PAMs to harvest waste heat from products with still getting these really high water yields. So now we move over to the dehumidification experiments. The first thing that we kind of had an issue with was chamber stability. So we had a slow response for our chambers. So what we did to compare it to our model is we just input our chamber humidity to our, we input this chamber humidity to the model. And that way we're kind of comparing apples to apples and comparing an ideal model with an unideal operating conditions for our device. The other thing we found is less than a 3K change in temperature versus the inlet and outlet. And what this shows is we're able to reject a significant amount of latent heat into the material and into the water running through it. And this produces a 26.3% reduction in cooling load by removing about 68% of the latent load on the device. So to compare it to the model, we saw a 9.3% difference in the model and experiments, kind of well within our bounds of reasonability, showing that we are able to kind of get close to these model dehumidifications that we saw in our device. And then again, yes, we use the inlet humidity ratio for the validation. So in summary, we started out at a material level. We found that cross-linking suppresses uptake, suppresses diffusivity. We found that enthalpy, unlike diffusivity and unlike diffusivity and uptake, are not affected by cross-linking. We found optimal hydrogel geometry is going to be 4 grams of lithium chloride, 6 milligrams of MBA, and we found that our surface flux is determined by this equation right here. And then on the component level, we were able to produce, we were able to conserve mass within 2%. We're able to demonstrate that atmospheric water harvesting devices we were able to show an atmospheric water harvesting device capable of harvesting 485 liters per meter cubed per day. And then we demonstrated a dehumidification device capable of reducing cooling load by about 26.3%. So finally, we're going to move on to the future work. What are the next steps in this experiment? So this right here is something that you really don't want to see in your hydrogel is we saw leaking. So what we did is we said, okay, like, is there any other negative effects of cross-linking? We made these hydrogels with extremely high cross-linkings, and we exposed them to really high levels of relative humidity. What we found was that synthesis of the water content is, synthesis water content is the first and foremost important cause of leaking, as you can see from this 50 milliliter sample right here compared to that 200 milliliter sample. And we found that cross-linking plays a significant effect in water uptake, and then salt content does. But what we were able to do is we were able to use a gel that was optimized, kind of where that 6 milligrams came from, is we were able to go up to about 93% relative humidity with 0 leaking. And if you're in conditions with 93% relative humidity, you kind of got bigger problems than your hydrogel leaking a little bit. So we were able to say, like, without unreasonable doubt, that our hydrogel wasn't going to leak in any of our operating conditions, and we were able to get through with it. The last thing that we saw, and this is a really interesting phenomenon, is we saw crystallization, this crystallization transport that's significantly faster than what our diffusivity model predicted. So this video takes place over 7 hours, which is roughly 10 times faster than you'd expect a crystal that size to adsorb. And it really got us thinking, like, why does this happen, right? And one theory that we came across is this crystal has, like, you can see these kind of pathways into it, and there could be something that the crystallization within the hydrogel is creating this porosity or some kind of wicking structure within the hydrogel. And that's causing this increased diffusivity through it. That's causing these really high diffusivities. But this is, like, highly speculative. So, like, with a grain of salt, no pun intended. But acknowledgements. I'd like to acknowledge my committee members, Dr. Jumin Zhang and Kangsha Menon, for helping me, kind of guiding me along the way, and obviously Bashir as my mentor. And then undergraduates Brandon Koso and Thomas Chu for helping me, Thomas with the experimental side and Brandon with that hydrogel leaking side. And then, of course, all my sponsors, all of the Energy Innovation Lab, and then all my friends and family that came to support me today. So thank you, and I'll be happy to take any questions.